Fantastic. Thank you.
Thanks, Lori.
Sure.
Great. All right, so we'll just dive right in then. Thanks all for coming to today's session. I'm sorry that both Kevin and I couldn't be there with you. Hopefully we'll be able to be there next year and tell you more things about how Phobos is developing. So today, as Kevin said in the larger session, we're going to give you an update about how Phobos has progressed over the past year or two, our successful conceptual design review, and I in particular are going to start off with pointing you at some tools that we've developed to do some simple science program development with Phobos. The reason we're doing this at the top is basically to give you a chance to, while Kevin is talking about more detail about the science that we hope, the big science questions that we hope to answer with Phobos, that you can be, insofar as you want to start to install and play with those tools. So let me try to go ahead here. Lost my mouse. Okay, click. Okay, there we go. Okay, so here's the outline, quick Phobos introduction. I'll give that. We'll give a brief motivation, which is basically just what I just said for today's session. And then I'll show you those tools. And then, as I said, you can start experimenting with those. Please ping us on our Slack channel. And then Kevin will go into more detail about the project update. And then we'll close with any questions, comments, etc. that you have for us. Okay, so just to remind everyone what Phobos is, it's a multi-object spectrograph, fiber-based for Keck-2. It uses star bugs as the positioning system. It's an optical spectrograph that runs from 310 nanometers to a micron at a resolution of about 3500. The total fiber complement is 1800. That's divided over 3 spectrographs. The spectrograph bank, I can't see in my mouse, so I imagine you can't see it either, but it's that those kind of beige boxes to the right of the Naismith port, which you're seeing at the left. And then the focal plane module is what deploys the fibers at the focal plane. There's a fold mirror that redirects the light so that we can have a horizontal focal plane that's beneficial for moving the star bugs around. And then there's a calibration system to the back. It deploys both single fiber apertures and IFUs. And we also will have a monolithic IFU option where all 1600-ish fibers that are not designated for sky or calibration are combined into a single of order 30 arc second on a side bundle. The throughput aim is to be above 30%. That's everything except for the atmosphere over the vast majority of the spectral range. The depth that we quote is about 24.5 AB magnitude in R band for signal to noise 1 after 1 hour. Okay, so the reason that we're presenting these tools today is to get you to start experimenting with how Phobos might be used for your programs. One of the kind of key outcomes from the conceptual design review was that they were very excited about this prospect of having large programs that could be merged together and multiple programs going on simultaneously, ones that might be using single fibers or IFUs or a combination of those. But in order to do that, in order to facilitate that, there's going to be significant tools that need to be developed, and those tools will get complicated quickly. And so we need to start doing that now, and we need good test cases for how to go about implementing that. So that's, we want your science ideas for Phobos. As part of our proposals that we've been putting into the NSF to fund preliminary design, the Keck SSC has allocated a certain number of nights as kind of a return on investment for that preliminary design. And in our upcoming proposals, what we're hoping to do is basically to use the proposals for that time as fodder for these kinds of programs that we can then see how they might be implemented with Phobos. And so you're encouraged to think about, if those proposals are successful and if that time is allocated, how you might use that time. And so that's the context for why we're presenting these tools now. And those 2 tools basically are an exposure time calculator and a target allocation observing planning tool. So I'll start with the exposure time calculator. This has been out for about 1.5 years or 2 years. And it's part of this package that I put together that also includes an exposure time for WFOS, or the iteration of WFOS as it was 1 year ago, if you're interested. It's called Synospec, and there's the read the docs link there. I'll post these slides on the Slack channel after this. And so the exposure time calculator really focuses on the throughput of the instrument. So here's the throughput curve. There are 4 different channels. That's why you see these 4 different effective humps in the throughput distribution. And they're colored, the dashed lines are colored by the throughput for each channel, basically. The top 2 lines are just the instrument starting at the ADC, and including 2 different options for how the CCDs are coded. And then the blue line includes the telescope. And I believe it's for the orange line plus the telescope through the 3 reflections from the mirrors. And so as you can see, we're above 30% as our requirement is for the vast majority of the spectral range, and it averages at about 40%, including the telescope. So once you have that, along with some aperture corrections, resolution, pixel sampling, extraction, all these kinds of details, the exposure time calculator will combine all those things and give you an estimate of what the signal to noise should be per fiber, per observation of a single fiber. So the read the docs page tells you how to install the package. It's Python 3 based. It should be relatively easy, but and we've had some on our science team use it already, but please definitely, one of the reasons we're advertising this is so that you can try to install it and help us troubleshoot all of those things. The options it includes at the moment is you can provide it a spectrum that you want to pass through it. You can make that the on-sky distribution a point source or a Sursic function. And you can define the general observing parameters, air mass, exposure time, etc. There's it's still very much in development. One of the things that we'd like to do is add a realistic Moffett PSF and to do batch calculations. So instead of doing 1 spectrum at a time, you can do multiple. The plot to the right is just a default output from the exposure time calculator. So if you just call it without any options, this is what it gives you. The top panel shows the sky spectrum in orange, and then the object spectrum in blue. Here it's just a constant AB magnitude spectrum, so that's why it looks like just a single line. And then the bottom panel shows the what by default is given as the signal to noise per pixel as a function of wavelength in a 1-hour exposure. You can, like as I said, you can change the exposure time, you can change the source distribution, etc. And the plot that it produces will reflect those changes. So that hopefully that ETC gives you a sense of how what are the reasonable things that you can observe with Phobos in a typical Keck allocation. We're also providing a target allocation planning tool. Again, this is the read the docs link, and I'll post these in the Slack. And so here the focus is to try to understand how you can distribute those 1,800 fibers to different and allocate them to the sources within the field of view. So I just want to talk through a little bit about how the focal plane is built and how the starbugs sample the focal plane. So at the top left is again a picture of that focal plane module, and you'll see that purple ring that's facing down that has the starbugs deployed on it. The middle image is just turning the face of that purple ring to face you, and you see this distribution, this hexagonal distribution of starbugs in the field. And so each one of those starbugs deploys what we call a payload for Phobos, and that payload can be a number of different things, and that's what's listed here, kind of in the bullet points to the right. It can either be a single fiber, a 5.5 arc second IFU that's composed of 37 fibers. It can be a single 1/3 of the monolithic IFU. It can be a 7-fiber calibration bundle, and also deployed our imaging bundles. These are bundles that produce a coherent image of a small 3 arc second patch on the sky that's used for guiding and focus tracking. As I said, there's 3 spectrographs. So the modules, the starbug modules each map to an individual spectrograph. And so 1/3 of the focal plane is devoted to spectrograph 1, the 1/3 to spectrograph 2, etc. And each of those spectrographs independently can be put in one of three modes. And that's basically the deployment mode that you want. You can either pick the single fiber MOS mode, the multi-IFU mode, or the monolithic IFU mode. And this table at the bottom right gives the number of apertures that are deployed in each of those modes. So in single fiber mode, for example, you'd have 546 single apertures that are deployed within the field for an individual spectrograph. And then you would multiply that by 3 for all 3 spectrographs. And then the bottom number there gives the total number of quote unquote active fibers in each mode. Those are the number of fibers that are then fed to the pseudo slit for that given spectrograph. So here's what the focal plane looks like if you put all 3 spectrographs in MOS mode. The individual orange points are single fiber apertures. The single green point that you see there is an IFU that's always deployed by spectrograph 1, which is to enable quick access to integral field spectroscopy of targets of opportunity. And then the gray hexagon to the right, blue hexagon to the right is the position of where the monolithic IFU will live. And the red circle outline is the 20 arc minute field of view for KEK2 the KEK2 Naismith port, which Phobos has full access to. So one of the tools that we've given allows you to basically look at the distribution of the apertures as you change the selection of which spectrograph deploys which kind of apertures. So here again is that same plot, but you can flip to all spectrographs being in IFU mode. And so here you see that the green squares are the individual IFUs, and then the orange spots are single fiber apertures that would be used for sky observations. You can mix and match. So here you can have one spectrograph in IFU mode and the other 2 in single fiber mode. So it allows you to play with one. If you have a single program that would use both of those, you can do that, or enable you to mix programs efficiently between different programs that would need different aperture types. This is one specific design of how the modules map between the focal plane and the spectrographs. This is the one that I think we'll end up preferring because it distributes the spectrographs independently across the full field of view. So spectrograph 1, when it's in a given mode sample, is the full field of view, but it might be more mechanically viable to do something like this, where each spectrograph effectively has its own zone of the field of view. So we'll have to study to understand which one is more beneficial. But if you have a science program that would benefit more from one or the other, we'd be interested to know that. So that's this focal plane layout tool. So if you download and install this Phobos reducer package, you'll have access to a command line executable that if you just call it, it'll show you that first plot that I showed you where all the spectrographs are in mode 1. And then if you call it with this, I guess I got my cursor back. I don't know if you can see it, but the command line that you would execute to get the specific plot that's being shown is at the top of the plot. So once you've decided what kind of aperture distribution you want, you can then give this tool called Phobos Make Plan a set of targets that it would then try to go and tile. That's the first thing it does, is it tiles the distribution of sources with specific Phobos pointings. There's a limited way that you can play around with that. The set of targets that I'm showing you here are just a set of quiescent galaxies pulled from the Cosmos catalog, and it automatically sets up this 34 pointing mosaic of how to target those. You'll notice that many of the pointings don't fill the whole field of view, and you can play around with how that's done. But this is kind of the default output for that tool. Once you have that, then you would call it again without the tile only tag. If I go back to that, you notice that I have this kind of dash tile only. So it only creates this plot if you have that option, and it shows where it's placing the tiles. Once you've decided that you're satisfied with where it's placed the tiles, you would call it again, and now it's going to go through each one of those tiles and allocate fibers to sources. And for each allocation, it gives you this output table. It tells you how the number of pointings that you require to get all the sources within that pointing, and then effectively how well you're using the instrument and how complete your sample is as a function of those pointings. And so the fourth column here, the COMPL, is the completeness. That's the cumulative acquisition of targets as you revisit that pointing again and again. So you can see it goes to 1. That's the default, is that it will always observe as many sources that you have as you have. The efficiency column tells you how many apertures it's allocated versus the number of available apertures. So in that top row, that first pointing, it tells you that there's 1,630 apertures that are available to be allocated to sources, but only 1,100 of those have been allocated. And the reason for that is most often because you can't, you can only put 2 targets so close together before the starbucks collide. And so there's a collision radius within which you can't allocate sources. And so the maximum efficiency, at least for this pointing, is 67%. So there's a whole 33% of targets that could be allocated to a different program as long as they don't collide with the existing apertures. And then the mean efficiency is just the cumulative mean of the efficiency as you go along. And so you see for this pointing, at least that's shown in this table, as you continue to revisit that, you're picking up sources, but you pick up fewer and fewer of them that just because of the collision radius mostly. Once you have an allocation, you can run this code called show config, which basically just shows you which targets have been allocated to fibers. So here the blue points are targets that have been allocated to fiber. The orange points are ones that have been missed, and it's probably hard to see, but there are light orange points where those are apertures that haven't been allocated to a source. So I realized that all went by really quickly. I'm happy to take questions now. We could also, but we'll transition over to Kevin after this. And as I said, I'll post these on the Slack channel. And today, or whenever you eventually use the tools, I encourage questions and any trouble that you have installing or using the software.
I've got a quick question for you.
Yeah.
So what's the closest approach between two two single fiber starbugs on the sky?
So at the moment, it's 10 arc seconds is the collision radius. We think it might end up being a little bit larger than that, but we're hoping it won't be. So at the moment, the software assumes 10 arc seconds.
And have you considered mounting the fibers off center inside the starbugs so that you can get them closer?
Yes, we have. And we haven't gone very far with that design. We're still, but that's something that we would want to test. There's an idea of having the starbug in the center and having 2 fibers to either side that could rotate and move around. So you always have these pairs of fibers. That's something we're considering, but we don't have that in this software yet.
And one more question, if I may. So what level of sky subtraction are you assuming for your exposure time calculator? And
at the moment, it's perfect.
It's okay.
So
nobody does perfect sky subtraction with fibers.
Of course not. Right. I mean, PFS is getting sub 1%. So we would, and some testing that Kevin has done, some really very nice detailed assessments of manga Sloan data, and we get 0.2% there. So we're hoping, we're expecting to do sub 1%.
Okay, thank you.
Hi, I have a question. Can you hear me?
Yes.
So I was wondering if you could say a little bit more about what the IFU configuration is like, and is that fully sampled, or is there going to be some kind of dithering to sample if you were looking at, you want to use the IFU to make a map of a resolved object, for instance?
Yeah, unfortunately, I don't think I have a slide on that in this package, but so it's 37 fibers. They're hexagonally packed. The fiber bundle itself doesn't have a full fill fraction, a 100% fill fraction, but it will be fed by a micro lens array that will have, of order 95% or above 95% fill fraction. So you shouldn't have to dither to just sample the interstitial regions of the IFU, but you might want to do that anyway to kind of subsample the of order 0.8 arc second aperture that each cell in the micro lens array will have. Any other questions?
I don't know if this sort of fits what you're talking about now, but for the actual starbugs themselves, what is the lifetime of each individual device? Has there been long-term testing about how they hold up over time?
That's a great question. Yeah, there has been, and we're pushing for more, and that's part of our preliminary design. So the starbugs are developed by the Australian Astronomical Optics Group in Australia, as the name indicates. They have an active starbug system on their UK Schmidt telescope. It's called Taipan. They did some testing for that, and they've done a lot of work basically identifying where they fail, how they fail, and how long they last. For Phobos, we expect the lifetime to be more than 5 years, and that's assuming that they're active much more than we expect them to be active at Keck, given the fact that Phobos will be exchanged for other instruments. So we're aiming for in the mechanical design to enable the individual starbugs to be exchanged. That's part of why the focal plane has this kind of modular looking hexagonal design. We want to be able to pull them out and have access to them pretty easily. But that's what we're expecting is of order 5 to 10 years lifetime for the starbugs.
Thanks.
So you mentioned multiple science programs with single pointings. At least that's sort of what I heard. Are you guys actually thinking about queue scheduling?
Queue scheduling is verboten. We want to be able.
That's why my question.
we want to be able to mix programs, which we expect that Phobos will have a few modes of observing, and one of those modes of observing will continue to be PI driven, where the PI has absolute control over what the instrument does. But as I showed in this one example, which has a huge number of objects in that 20 arc-minute field, you're only at most, it was allocating 67% of the available apertures. And so we think this is a good thing in the sense that we hope that eventually what we have is a database that, say, has all LST sources in the sky everywhere. And anywhere that you would point, there would be something that someone would find interesting, and that there would be a spare fiber, quote unquote, spare fiber database that could be, that a spare fiber could be allocated to that target. How exactly that works, that's part of the reason we're bringing this up now, is we want to be able to develop tools that will make that just a simple click of the button, is that things are allocated, and so that there's no wasted time. A PI doesn't have to think about it. They don't have to feel like they're wasting their time or losing their own observations. But then, of course, the second mode where you have two PIs that kind of co-propose for a synergistic program that it gets observed simultaneously. There are examples of this in Keck that has happened already with, like, for example, the Halo 7D program, where they were halo stars observed at the same time as they were getting rotation curves of galaxies with DEIMOS. But we want to make that easy, and we want to make that as easy as possible.
So you sort of treat them as target of opportunity objects.
Yes, but
So
well,
the idea is
you're
not going to have unallocated fibers, even
yes. If at
you
all
can't-
possible, no.
you can't satisfy anything else within the science program for that particular pointing.
Right.
I mean, it seems like a waste otherwise.
Yeah. And also say that this is, one of the other things that we've been advertising in our proposals for funding for Phobos has been some fraction of fibers that will always be allocated toward US community driven targets. Not that they would drive where the pointing would be, but that effectively they would be, they would have a higher priority in that database of targets that could be allocated to spare fibers. But all of this is still kind of being worked out, exactly what that will look like.
So if I may ask one more question.
Please.
So how do you reconfigure the spectrographs for IFU versus single fiber versus the other mode? Is that something that happens automatically?
It's a good question.
Allows you to interleave different programs within a night, or?
So at the moment, no. It's a really good question. So it's hard to see here. We've got better pictures of this, but there's a cable that comes out and connects to another cable here. So there's basically a gang connector between fibers, and there will be 3 ports that each one will feed to on this kind of rack that you see coming here. Am I sharing my screen? I'm not sure I'm sharing it anymore. Okay. And so we envision it now, at least in the current design, as a nightly operation where it's for the night it's decided which mode each spectrograph is in, and then the next night it can change. But we're hoping to actually develop some optical switch technologies that would make that a lot simpler. And so you actually might gain in terms of your efficiency in two ways. One, that you might be able to couple in the optical switch better, but also it would make that exchange much faster. Josh, go ahead.
Yeah, just a question. In the current configuration, it looks like you don't have any form of field derotation. So are the starbugs walking around to follow field rotation as the telescope tracks? And if so, does that provide, does the speed provide limits on where you can point in terms of near the zenith?
So the second question is moot. There is a rotation. This blue element here kind of rotates and also kind of moves out as the ADC goes through its motion.
Okay, thanks.
Yeah, good question though.
On a similar-ish note about movement, for the starbug or fiber placer thing that you showed, has any thought been given in how fibers are arranged from one state to another without tying themselves in a knot?
Yes, the Taipan is huge for us in terms of kind of working through all of these issues. So AAO has some very sophisticated software that routes how the starbugs move and how they make it to their target position. It's more complicated with Phobos because the density is a little bit higher in terms of the number of starbugs per square millimeter or whatever. But they have those routing algorithms in place.
Sorry, I have one more question about IFU modes. This is probably me just not understanding things, but when you have it in monolithic IFU mode, do you have 3 monolithic IFUs then for each of the spectrographs? Is that, or is there one monolithic IFU that goes to each of the spectrographs? Sorry.
It's definitely unclear, and I apologize for that. And the reason it's unclear is because we're kind of uncertain exactly on how we're gonna construct the monolithic IFU. The idea is that it will be monolithic in the sense that all of the fibers will be collected into a single coherent on-sky region. But we think it might be easiest to design it in a way where we have 3 separate 547 fiber hexagons that are then joined together to create the monolithic IFU. So that's the ambiguity there, is that they are 3 separate entities that are just joined together as close as we can get them in the design, and it will be possible to select the monolithic IFU or the monolithic mode for one spectrograph and not the other, but you wouldn't do that because you'd only have this 547 fiber thing over at the edge of the field, and then you'd have all the other things that you could allocate over here, and you wouldn't be able to move the monolithic thing. And so we expect that if you're in monolithic mode, all 3 spectrographs will be in monolithic mode. I'm not sure if that was, I hope
that makes sense. And I'm just, from the perspective of someone who likes nearby galaxies, for instance, that this might result in you having the ability to have a map that's nearly an arc minute across or something with all 3 of the monolithic IFUs operating at once.
Oh, sorry. So I should clarify that too. So this 37.6, that's all 3. That's not per one. So it's right. So it's, I mean, it's about a quarter of Muse, basically, is what.
Got it. Makes sense. Thank you.
Yeah.
Where's your positioning camera?
So there's there's an acquisition camera here, and then beyond that there's the guiding bundles that keep focus and guiding that are within the field itself. That's these red points here. You're muted.
The first camera is the one you use to set the pattern of the starbugs.
Oh, sorry, you're talking about metrology cameras. So
yes.
yes, yeah. Sorry. So those are I think they're on the ring here. So they look up at the focal plane from below. Yeah, that's very important to be able to register where the star bugs are on the focal plane.
Kyle, there's a question in the chat from Joel. Will PIs have to submit their fiber configurations ahead of their observing night? And will those configurations need to be vetted by tech staff before going on sky?
Those are great questions. The idea, at least, is that, you know, in just the same way as that they're introducing these observing blocks, scheduling things that happen at the telescope, but you can change those, you know, right before you would go. And so that's the same thing would happen with Phobos, is that you would use this tool, create a configuration file, and then you could immediately send that configuration file to the telescope to configure Phobos. So there, you know, there's a process there, but you won't have to submit them, you know, days ahead of time.
I think our philosophy is that the PI knows the right answer. And so the software that we want to develop is going to make the best possible suggestions, but we want the observer to make final decisions and have that control.
Yeah. So let's transition to Kevin.
I'm actually going to suggest just wait, since those were great questions. I can say a few words, but I don't want to stop the discussion. Maybe I just did.
I'm sure it's my fault.
We'll come up with more questions. Don't worry. You can
All right. Sounds good. Okay, so we're doing this a little bit in reverse of what we would normally do, which is that we got into the weeds and into the meat first, because we wanted to give the folks at home an opportunity to start actually playing with some of the tools that Kyle just introduced. And we figured that many of you were already familiar with Phobos, and so the kind of going back and talking about the science motivation may not be all that interesting, and yet we know there's lots of folks in the audience who are just encountering this instrument concept for the first time. So given the time, I don't want to talk too long, and I just want to hit some of the science motivation and some of the larger sort of key science reference programs that we've defined in our science team to help kind of spur you on to think about your own potential programs and your interests in the scientific output that we hope Phobos will deliver. And then if there's time, I'll talk very briefly about an update on the project, and I'll walk you through the design a little bit more, although I think we've covered a lot of ground and a lot of the details people were interested in. So there's my outline. You know, as we think about this instrument, we've really sort of divided the scientific landscape into two pieces. And we realize that there's this one that we call the cosmic ecosystem, which is a theme that connects many of the large programs that we think are exciting for Phobos across many scales, across all kinds of redshifts. And so that's going to be a theme that I'll talk about, and many of the programs we developed are in that sort of cosmic ecosystem theme. But then it's also, I think, important to say that, you know, Phobos can play a really significant role supporting the larger community efforts underway to understand the dark sectors. So here I mean dark energy and dark matter. And so I think, you know, that's in some ways a supporting role, but a really important one, and connects us to mission goals of other facilities and other instruments that are coming online. I just want to acknowledge our science team. This is a couple of the key people who have been involved in thinking about the scientific landscape that Phobos will be entering. We're expecting first light at the end of this decade, so 2029, 2030. So we've been thinking a lot about what kinds of facilities, what kinds of new ways are we going to be thinking about things at that sort of time frame. And the folks on the screen here have been really important in trying to get our minds into the future and think about what's to come. And of course, JW, ELTs, and then Rubin and Roman are big in our minds. So let me very briefly mention some of the design reference key programs that the science team and the folks that whose pictures I just showed have developed. And the goal here is to not only understand what Phobos can do, but also drive requirements that can help us make sure that we're designing an instrument that is as powerful as it needs to be. So within this sort of cosmic ecosystem framework or theme, we have a couple of programs that are worth highlighting. We think that these would be multi-year collaborative kinds of programs. They could be quite significant in terms of the time that they would take, but I think they would also deliver some really exciting things. So the first to mention is an IgM tomography case. And here the blue wavelength coverage that Phobos provides lets us go down to lower redshifts than other competing facilities like PFS. And we can also make use of our high density sampling on the sky to get down to megaparsec scales in terms of being able to sample what's going on in sort of halo scales in the IgM. Coupled with this is the idea of looking at the CGM, so the circumgalactic medium, in emission. And this is one of the key drivers of the IFUs and the sizes of the IFUs. We think that there's the potential to actually see high ionization emission lines in emission using our IFUs. And so this idea of going very deep and combining IFUs and single fiber programs lets us realize a program like this. So here the goal would be to actually trace out the kinematics and the abundance patterns around a set of, say, 100 galaxies at redshift 2. Then we're interested in building a very large Ensemble UV spectral database of galaxies at redshift 2. And we want to be able to have a large sample, something like 15,000 galaxies, spanning a range in mass and other galaxy properties in order to make stacked ensemble spectra that can provide very high signal to noise diagnostics of stellar and nebular abundance patterns and even kinematics. So the ESO Vandal survey is one example of this being done right now on VLT. Obviously, this has been bread and butter for Keck for a long time. We think Phobos is really going to take it to the next level. And then, we're interested in this ecosystem also in terms of the kind of fossil record that it imprints on nearby galaxies. So we thought a lot about M31. And here we're particularly motivated by the scale of the Phobos field of view compared to the scale of the M31 disk. So something like PFS, whose field of view is also shown on this slide, is quite large. It's going to be great at studying the halo of M31. We think Phobos, with its smaller field and higher density, is really going to give us a fine-tuned look at the stellar disk. So we're interested in doing some of the things that are happening now in the Milky Way in terms of resolved stellar work, but now taking that information and getting it from M31. We also think that there's a time domain capacity that Phobos will be really exciting for. And one that we've thought a little bit about is following up Kilonova. So this connects to the cosmic ecosystem in terms of enrichment on basically the smallest scales. So being able to follow up potential Kilonova candidates, confirming those candidates, and then also getting very early blue spectroscopy in order to understand how enrichment is happening, how those heavy elements are being created. So you can see that takes us quite a range in redshift, quite a range in scales. And the theme there is really understanding interconnected cosmic systems. Let me just mention the dark sector. we have an important role to play in terms of calibrating photometric redshifts for Rubin and Roman. And so the same program, or a very similar program to what I described for being able to stack and get high signal to noise spectra of redshift 2 galaxies, a very similar kind of program is needed to get redshifts for PhotoZ training. So we can almost do a 2-for-1 here and satisfy the needs of both programs at the same time. This is, perhaps a little blasé science, just getting lots of redshifts, but it's absolutely critical to the cosmology community. And if you think of it in terms of being able to double the cosmological per night value of LSST, that seems like a pretty important role for Phobos to play. And even compared to some of the other instruments on the horizon, our depth, our wavelength coverage is unique. So we have a important role there. And then I think we're well suited to studying local group and nearby dwarf galaxies, getting kinematic information and putting constraints on dark matter. Okay, so I don't want to talk a whole lot more because I want to be able to have a little bit more discussion. So I'll just quickly run us through the design in case there's a few other details here that might be of interest. So let's do a little walkthrough. Kyle mentioned that there are these two main components. There's the focal plane module that fits into the Naismith port, and then there's the bank of spectrographs. You can see that the focal plane module is on rails, so you can actually roll it back and put in another instrument. Phobos doesn't have to be installed all the time. The spectrographs, however, are fixed. They're going to stay in that location on the Naismith deck, and we really want them to be completely stable, unmoving, not changing in temperature, and so that's part of the motivation there. You can see that they're really close together. That allows us to have a short fiber run, which is important for UV transmission with the fibers that are available on the market. So light's coming in from the Keck Naismith focus. It hits the first an ADC. The first two elements of the ADC, atmospheric dispersion corrector, are actually mounted inside the Naismith barrel. Then there's the fold mirror that Kyle mentioned, which directs the light upwards so that the starbugs can walk on a horizontal surface and face down. Gravity holds them onto the plate in addition to the vacuum that they have inside themselves. And so that's a nice thing that keeps the system stable. The light passes through the fibers up into this fiber run, and then it's distributed into the spectrographs as Kyle described. We also are quite serious about sky subtraction. we do worry a lot about it, so it's important. It's good that it came up. And one of the things we think is going to be important, one of the things we're hoping to improve on for this instrument is really excellent calibrations. So we're going to be building a dedicated dome-based calibration system, and we're working on a new set of lamps and possible screens for the dome light. But you can't do dome calibrations in the middle of the night. And so we've designed this onboard system that can provide calibrations whenever you like. And we want to tie these two together. So you get an absolute calibration from the dome, and then you're constantly able, if you want, for your program, you can update and get a relative calibration using the onboard system. So part of our effort to really make sure the instrument is well characterized so that we can reach the depths that we want. I think I'll skip this just to mention the spectrographs have 4 channels, and they're really inspired by the DESI design, not quite the same, but very much using heritage from DESI and some new technology as well, these FSE gratings, which give us some excellent throughput. We've talked a lot about the starbugs, so I'll skip that. Let me just mention the status of the project. So we've had our conceptual design review, as I mentioned, in July, and we're looking now to fund preliminary design. So we have an Australian LEAF grant, which is pending, and then we're looking to submit to the NSF in several months and hope to get funding for our preliminary design. We're still aiming for a first light in 2029. Up on the slide there, an invitation to join us in various communication channels, mailing lists, Slack, we have wikis, we have meetings. Please get in touch with us if you're interested and would like to engage more in helping to define what Phobos looks like. And finally, let me just thank the Phobos team, number of institutions, a number of really important contributions from people, and we're just delighted to have this excellent group of engineers and scientists working with us to figure out what Phobos is going to be. So thank you. I think we have a few minutes left, so we're happy to take further questions, and especially if there see is kind of steps. All right, everyone's busy in their Python terminals running target configurations.
What kind of fibers are you using to get down to 310 nanometers?
These are polymicro PBP something something. It's
So they're just
same...
standard fused silica that are dehydrated, basically, right?
Yeah, there's nothing fancy about them. The way we've dealt with the transmission losses is making the fiber run as short as we can.
How long is the fiber run?
15 meters.
15 meters.
Yeah, these are the same fibers we used in Manga and Boss. I think they're the same that are used in DESI.
What does instrument recovery look like if vacuum is lost on the Starbucks? Or is the plan to never lose vacuum?
No, we have to plan for everything. So the Taipan folks have engineered a pretty sophisticated system that they call the bug catcher. And Kyle, you can help me out with details here, but you know, for Taipan, the focal plane is moving around quite a lot. I think is it prime focus?
I think so, yeah.
So, you know, it swings around. And so they really had to worry about this. And I think it's a multi-layer system so that the set of bugs that are a problem can actually be lifted off the focal plane and sort of sucked back into place and then remounted. So yeah, it's definitely an issue, and you know, we want to be able to recover from any kind of issue like that quickly.
And that's one of the big motivations for having it horizontal. You know, for Taipan, as it swings and it becomes more vertical, if one loses vacuum, then it can knock into another, and you get this kind of cascade. And so it's really important to us to have that horizontal focal plane.
So I know the existing Starbucks are rotationally symmetric about their axis. It's just a single fiber. You're going to have IFUs in there, which means you care about the clocking. Doesn't that mean a whole new and different positioning set of software efforts beyond what AAO has done?
I can take that.
Yeah, go ahead.
I think that my understanding is that there are 3 backward illuminated metrology fibers in every Starbug that is deployed on Taipan and is in our current design. And so I think that they are currently tracking the clocking of every Starbug in addition to the translation. So you're right, except that I think it's already being done, and it will be important for us. If I could just add one thing, that the fact that we have IFUs might provide some kind of solution to your suggestion that we have offset fibers, because what if every single fiber had an IFU, but we just populate the single fiber ones, just have one fiber at the edge of the ring that's populated? I'm not sure that buys us as much offset as we might be able to get, but it could be a solution and would allow us to just make the same bug over and over and over, the same payload, just different numbers of fibers populating the IFU.
So they do indeed have 3 illumination tools, LEDs or fibers, but I don't think they care about the rotation. They measure it, but they don't care. And I think it affects the
You
positioning.
may be
time.
right. I
But
wonder
things
if
may have
they might.
changed.
I wonder if they might care because of cabling. Just twisting the cabling too much may be an issue. But I hadn't put together that they shouldn't care. So why do they have those 3? But you're right.
Well, I think that I may be wrong, but I think they do care it because I think the piezo's are directional, and so they have to rotate them and then move them and then rotate them and move them, and so they need to know the rotation in order to move them in a known direction.
Yep, that's absolutely right, Kyle. You reminded me. Thank you. So, I think some of the early Starbug prototypes, actually, they tried mounting the fibers on the outside of the Starbug, which is also something to look at for closest approach. Then it would only be the, the fiber and the cladding.
Yeah.
Well, like I said in the chat session, I think this is an extremely cool project.
Thank you. And
Best of luck with it.
thanks so much. And thanks to everyone for joining today. We want those science program ideas. So if you have thoughts, get in touch with us, please.
Great. Thank you so much, Kevin and Kyle.
Thank you.
We're going to be leaving this breakout session from the main room to go back to the main session. We have 2 more talks.